For this lesson, we'll be going over two-port networks. A two-port network is a circuit with 4 accessible terminals where 2 terminals are inputs and 2 terminals are outputs. The two-port network simplifies a set of elements such as resistors, inductors, capacitors, etc., and displays them as a box. If you look at the illustration, there's a unique configuration of resistors, and it's actually transformed or illustrated as a box to indicate this is a two-port network. So a question you may be asking yourself is, okay, what is so special about two-port networks? Well, the overall goal about a two-port network, by breaking down circuits into boxes, it allows engineers to easily calculate the response of a network when signals are applied to the terminals. So if you have a big circuit and you want to break it down to individual boxes, this setup kind of allows you to do that. Now, some of your two-port networks may consist of filters, transmission lines, transformers, and BJT signal models. These are not the only two-port networks, however, these are some of the most common ones. Now, each network gives you a list of parameters, and these parameters are based on which type of network you choose or which parameters you're looking for. And we'll go over that next in the later slides. So as stated in the previous slide, the two-port networks are represented by a set of parameters. The 3 common ones we're going to go over is impedance, which are your Z parameters, your admittance, which is your Y parameters, and then your hybrid, which is your H parameters, and that one's going to be a little bit more unique, and you'll usually see that commonly known through your BJTs or your small signal analysis models. Now, there are other two-port networks out there, such as inverse hybrid, transmission, or chain. We're not really going to go over those, but those do exist. Now, the 3 common ones we are going over, those equations are listed in your FE handbook. So if you have that, the illustration below is taken from the FE handbook, and it kind of gives you an idea of what equations you can use and how to find your parameters. Okay, so let's go over our first one, the impedance two-port network. This is also known as your Z parameters. Now for this lesson, I want to show you a very unique way of how to solve these parameters. It's not too complicated, it's actually very simple. It's a crude way of showing you, but it's a way that everyone can understand. Now, in the illustration below, I have 4 different layouts. And based on the layout and what parameter I'm going for, I might introduce a current source or voltage source based on whatever book you're using, but I'm going to base what I'm showing you here, I'm going to use the current source for our impedance two-port networks. And in the example, I'm going to show you how I solve the parameters based on using these layouts. Another two-port network would be our admittance network, and this is going to be your Y parameters. Now this one is going to be very similar to your Z parameters or your impedance network. However, I'm going to also show you the same unique way of trying to solve it, but instead of a current source, I'm going to implement a voltage source and a short. And again, I'm going to show you this in detail in the examples. The last two-port network we're going to look at is known as the hybrid. Now this one's a little bit more difficult and a little bit more unique compared to the other two. See, for example, your previous one, your Z parameters were all in resistance or impedance. Your Y parameters were at admittance. Now the hybrid has parameters that are, one is resistance, one is in a ratio, one's a gain, and one is admittance. So this one's going to be a very unique compared to the other two. And this is the one that usually trips people up very much so. Now this one you'll usually commonly see among small signal models or your BJT AC models. And we're going to touch base and do an example problem of this particular one just so you know what it looks like and to get your feet wet. All right, for our first example, we're going to jump right in and try to find our Z parameters for this particular two-port model. Now our Z parameter is going to be our impedance, which means all our Z parameters are going to be in resistance. Now, like I said in the slides, I'm going to show you a very easy and crude manner of finding these parameters. I'll show you a very crude method, but it seems to work no matter what skill set you have. So if you're very new to two-port networks or expert, this is a method that will work. So the first thing I'm going to do is let me go ahead and copy this two-port network so I have something to doodle on. Something I want you to be aware of, anytime I have a current equal 0, for example, I2 equals 0, that means it's going to indicate an open. So for I2, which is this side right here, it's going to be an open. Same thing with the next parameter, I1 equals 0, that means it's going to be open at the input ports. What I'm going to show you is I'm going to input my own current source for every single one of these parameters. So for the first one, since I2 equals 0, means I'm going to put a current source right there at our input, just like I showed you in the slides. So and I'm going to make up my own current. I'm going to call that 5 amps. Now, I'm going to go ahead and leave I2 open, and I want to plug and chug our V1 over I1 to find our first parameter. Now, here's how we're going to do this. So, I want to find what V1, and that's right here. I want to find what it is right here. Well, we can do this by breaking down the circuit and using simple Ohm's law. This is not difficult. It's going to be very easy. Okay, so let's just say we had these two resistors together, the 25 ohm and the 75 ohm. Well, put together, those are going to give us a 100 ohm resistance. And that's in parallel with a 50 ohm resistor. So if we redraw this in a very simplistic manner, hopefully my chicken scratch is not too bad. It's 100, that's 50, and then we obviously inputted our current source. That's 5 amps. Okay, and we want to know our voltages right there. Well, there's a way we can do this. Very simple little current divider rule here. We can say 5 amps multiplied times 100 ohms over the total resistance, which is 150. And tell you what, see if I'll just go ahead and put it right there. A little simple plug and chug in your calculator here. It's going to give us 3.33 repeating amps. Now we have our current going through the 50 ohm resistor. Now to find our voltage, it's V equals, that's going to be V1, I times R. So which means that's going to be 3.33 amps multiplied times 50 ohms. Because remember, we're trying to find the voltage just right here. And plug and chug that in our calculator. It's going to give us approximately 166.65 volts. Okay. Now here's the good part. We now have V1 and we have I1. Plug and chug in that one equation right there. It's going to equal Z11 equals V1 over I1. And I'll put it right here, just make it easy on us. It's going to be 166.65 volts over the current we determined to use. So it's 5 amps. So that's going to give us a final answer of 33.33 ohms. So that right there is going to be our first parameter. So I'll put that right up here. Okay, let me clean this up so we can go again. Okay, same song, different verse. Now, instead of putting a current source at the input side, now I'm going to put on the output side because I1 equals 0. So that means there's going to be open at I1. So I'm going to do the same thing. Current source, an ugly current source, 5 amps, because I like to keep it simple. Okay, now this one, same thing. If you're looking at it from this perspective, we have the 25 and the 50 ohm resistor right in series with each other. So we can add those together, giving us 75 ohms. Well, that's pretty simple. So we need to find V1, and looks like we already have I2. This one's already I2, which is that guy right there. So now we need to find the voltage right here, V1. So we need to find the voltage again at this 50 ohm resistor. Now this one's going to be a little bit different, be a little bit easier. Anytime you have two same resistors in parallel with each other, they're going to share or split perfectly even whatever current's going through them. For example, I have 5 amps going this direction. Well, 2.5 is going to go this way. 2.5 amps is going to go this way. So there's going to be 2.5 amps going through the leg right here, and then 2.5 amps going through this leg. That one's pretty simple because I just have two 75 ohm resistors in parallel. So I know what the current is flowing through the 50 ohm resistor. Now I need to find the voltage. I know that V equals I times R. So I have the current, which is 2.5 amps, and I have the resistance, which is 50 ohms. Okay? And plug and chug that in our calculator is going to give us a very simple answer of 125 volts. So I have V1, I have I2. So let's go ahead and plug and chug that in our equation right here. So put it to the side again. Z, 1 of 2 equals 1 over I2. So that's going to be 125 volts over 5 amps. And give us a final answer of 25 ohms. So I'm going to put this guy up here. 25 ohms. Okay? same song to verse, we're going to do it again. Let me go ahead and clean this up. We're going to do this guy right here, Z2 of 1. So V2 over I1, and we want an open at I2. Over here, and a current source over here. So we're going to do the same thing again. Make my own current source. And usually an ugly one. 5 amps. I like to keep it simple. Alright, same thing again, 100 ohms. Noticing a pattern I see. Okay, so we want to find V2, which is right here, because it's the same as this leg right here. V2, and we already have I1, 5 amps. Okay, so same thing as earlier. Now this one's a little bit different. We need to find the current going through this leg, and then we can find the voltage. Now earlier, in the previous problem, we found this guy right here would actually have 3.33 amps, which means this guy would have 1.667 amps. So we know the current flowing through the 50 ohm resistor, and we know the current flowing through the 25 and the 75 ohm resistor. However, I need to find the voltage right here. So just like last time, V equals I times R. So V equals 1.667 amps times 75 ohms. And plug and chug that in our calculator is going to give us an answer of, same thing as last time, 125 volts. Z2 of 1 equals V2 over I1, which comes out to be, make that a little bigger, 125 volts over 5 amps. Going to give us 25 ohms. 2 of 1 equals 25 ohms. Last one. So I'm going to clean this up one more time. We want to open at the input, which is I1, and we're going to do the same thing as we did in previous problems. We're going to put our own current source right there. And same as last time, 5 amps. All right, so we want to find V2 over I2. So V2 is right there. And I2 is right there. We already did that one. Very simple. Well, just like last time, we already know 2.5 amps is flowing through that resistor, and 2.5 amps is flowing through these two resistors. Reason being, 25 plus 50 equals 75, and since you have two 75 ohm resistors in parallel, you split off the current evenly. V equals I times R, same as always, is 2.5 amps multiplied by 75 ohms. Give us V2 of 87.5 volts. And then it says Z22 equals V2 over I2. So, slow down that way, it's legible. 187.5 over 5 amps. Going to give us a final answer of 37.5 ohms. So now we have our Z parameters. I did that. Now there are other books that show you different methodologies. This seems to be the simplest and easiest way, no matter which two-port network I have that has resistors or inductors in it. What I'm showing you here is very crude, but I'm showing you a method that works and something you can do in less than 6 minutes. So we now have our Z parameters for this two-port network. Okay, let's do the same thing again, but this time let's do it for another network, but for admittance or our Y parameters. All right, for our next example, we got something that's a little bit more trickier, but we're going to go overcome it with the same methodology. Now for this one, we want to find our Y parameters, which is going to be our admittance. So same thing as last time. I want to go ahead and copy our diagram here. That way I have something to doodle on. Okay, but instead of current sources this time, we're going to use voltage sources. And we're going to use the same method. So I1 over V1. And we want V2 equals 0. So V2 equals 0 means it's a short. So we're going to put a short right there. And that's V2. Now for V1, I'm going to go ahead and add a voltage source. Nothing fancy, just something simple. And I'll tell you what, this time it's going to be 10 volts. I'm just picking a random number just because something I feel comfortable with. Now this one, we want to find I1 over V1. Well, V1 is right here. We already know what V1 is. I1 is the current go in this direction. We can do this in a few ways. Since we shorted V2, the 10 ohm resistor and the 15 ohm resistor are in parallel. So that means these two guys are in parallel, making a total resistance of 6 ohms. These two guys together now create one resistance of 6 ohms. So now we can find our total current just by using simple Ohm's law. We have 6 ohms plus 5 ohms gives us our total of 11 ohms. Simple. And then using Ohm's law, I equals V over R, which comes up to be 10 volts over 11 ohms. It's going to give us an answer of 0.909 amps. Now that's the total current going through this whole circuit. Now that we have total current, that is the current that's flowing through this 5 ohm resistor, and then it splits off between these two resistors right here. So current flowing in the resistor is going to be current flowing out of the resistor. So that's actually I1. Same thing as last time, we're going to plug and chug that value right in this equation right here. So admittance 1 equals I1 over V1. So that's going to be 0.909 amps over 10. And that's going to give us our first parameter of 0.0909. And it looks like that's a positive based on the current flow direction. So there's our first parameter. Let's do the next one. This is where it might get a little tricky. Do the same thing again. Now it says V1 is 0, which means there's going to be a short right here at V1. And same thing, I want to add a voltage source right here. An ugly one, as usual. And we're going to make that 10 volts as well. Big font of 10 volts. Now, we want to find I1, which is current flow in this direction, I1, over V2. Well, we got V2. So we need to find the current flowing through this 5 ohm resistor. Same thing as last time, we find the total current. It's pretty simple. So 5 ohms in parallel with 15 ohms. It's going to give us a total resistance for these two guys of 3.75 ohms. Okay, so our total resistance is going to be 3.75 plus 10, because the 10 ohm resistor is in series with this source. Make it easy on us. Our total equals 13.75 ohms. Well, current's very simple. The total current is going to be 10 volts over 13.75 ohms. Most of this is just Ohm's law. There's nothing really much to it. And plug and chug that in our calculator. Our total current is going to be 0.7272, and that's going to be repeating. That's amps. So then we have the total current going through this particular resistor, and then it branches off right here. Well, when you find the current goes through this 5 ohm resistor, very simple current divider rule, which is going to be 15 ohms divided by the total, which is 20 ohms. And then we're going to multiply that times our current, which is 72. Let's see if I can actually make it look somewhat pretty. Amps. And plug and chugging that in our calculator is going to give us an answer of 0.5454. All right, so that's how much current is flowing through that one resistor in this direction. Because see where the arrow's pointing? It's going down this way. So I have 0.5454 amps flowing through that one resistor. So that would actually give it a negative, because I1 is originally going inward, or this direction. However, our current is now going the opposite direction, so that's going to be a negative 0.5454. So always be aware of the arrows. That's where this area will trip some people up. Well, now that we have I1, we have V2. We can plug and chug that. It's very simple. So Y, 1 of 2, equals I1, which is negative 0.5454 amps, divided by V2, 10 volts, gives us an answer of negative 0.05454. And we'll just stop right there. So that's going to be a negative 0.05454 5, 4. That's also an S. I'll tell you what, that way you know it's an S. So this is the only area that's going to probably trip you up as admittance, is knowing which is going to be negative and which is going to be positive. You just got to pay attention to the arrows. In the models, they're going to show I1 with an arrow pointing that direction and I2 with an arrow pointing that direction. So be aware of that parameter. We have V2 equals 0. So that means there's going to be a short right there. Same thing. And then I1, I'm going to put my voltage source again. 10 volts. Like I said, I just need to pick one and stick with it. Just keeps it simple. This time we want I2. So we want I2 over V1. Well, there's V1. So same thing as last time. I'm going to go ahead and find our total resistance, which is going to be, well, based on the previous problem, we already know what those two in parallel are. That's 6 ohms. So, and our total current going through this guy was originally 0.909 amps. And that's about what it was originally, the I total going through this whole circuit. However, we want to find the current going through this guy right here. Current divider rule, which is 15 over 10 plus 15, total current, times 0.909 amps. And plug and chug that in our calculator is pretty simple. It's going to give us 0.5454 amps. Ah, that's very good. Same amount of current going in this one as in the previous one. However, be aware, I have current flow going to the right and down. However, I2 is going inwards, which means it's going the opposite direction of what I2 is originally stated in the model, which means this is going to be a negative 0.5454. So that's actually a negative, just based on the current direction. So when you draw it out, be aware of which current direction you're using. And we can plug and chug that in our equation. So we have Y21 equals I2 over V1. And we know I2, which is this guy right here, negative 0.5454 over 10 volts. And that's pretty simple. You just move the decimal point over. It's going to be negative 0.05454. Very similar to the one we had before. So we'll go and plug that guy up there. Negative 0.05454. And that's admittance. All right, last one. Let's see if we can do it one more time. Okay, last one. V1 has a short, so I'm going to put a short at V1. And then I'm going to do the same thing. Voltage source one last time. That's V2. And we'll make that 10 volts. Surprise, surprise. And we want to find what the current is at I2. Well, we know that's 3.75 ohms when you put those two in parallel. So our total current is going to be, or excuse me, our total resistance is going to be 13.75 ohms. And we have 10 volts right there, so I2 equals, and this is going to be also your I total, it's going to be voltage over resistance, so it's 10 volts over 13.75 ohms. So it gives us a total current of 0.7272, and that's just repeating. All right, plug and chug that. It's going to be 0.7272 over 10 volts. That's going to give us a final answer of, and all you do is move the decimal point over, 7272, and that's, there we go. Current is flowing the right direction, so that's going to be a positive number anyway. Well, that one was pretty easy. Usually the first one and the last one are usually pretty easy. It's the middle two that usually trips people up, because whether it's the current direction or just where you got to find the current in the equation. This one is usually at the beginning. Let's do one more problem, but we're going to do the hardest one next, which is our hybrid model. All right, for our last example, I picked something that's a little rather fun. Now, we already have the parameters set up for the H parameters for this particular two-port model. But we're going to go ahead and see if we can analyze it and show you how to kind of use the hybrid model parameters and trying to find a particular value. For example, we're going to use the same model and find what the load resistance is. In other words, RL right here. So we're going to go through and see if we can go through this one step at a time to find what that resistance is. So I'm going to do the same thing as last time. I'm going to copy my picture here. Now I have something to doodle on. Based on this, on the BJT video, however, I want to actually go through each parameter step by step. H11 is your input resistance or input impedance. H11 is always in ohms, and that's your input resistance. So for this one, it's 480 ohms. So right there, 480 ohms. Okay. What I have is H12, which is our voltage ratio. Now right there, it's usually a very small or minute amount. For this one, it's 4.8 times 10 to the negative 4. So you multiply that value times voltage, and that will give you your voltage ratio. Again, this is usually a very minute amount. Sometimes in most of your models, it's not even considered because it's so minute. And I'll show you why when we do this analysis. But for now, I'll just go ahead and write it in there. 4.8 times 10 to the negative 4. Okay. Next one is our current gain, also known as beta if you're doing your BJTs, but it's 150. So that guy right there, which is beta, 150. And again, that's your current gain. Next is going to be your admittance. And this is usually your output admittance, which is, S, but it's right here. And again, usually this is so high, it's usually negatable in some of your models. For example, this one is 10 times 10 to the negative 6. Well, if this was a resistance value, you do the reciprocal of that, it's going to give you 100 k ohms. So whatever you have right here, it's in parallel with a 100 k ohm resistor. So usually in most of your models, even that's also taken out. So sometimes you'll have this part taken out and that part taken out when you're doing some of your analysis. But for now, we're going to leave it in just so we can get a very good understanding as far as how this model works and how these equations interact. Step by step on the previous ones of how to use these particular equations. But on this one, I want to utilize these equations right here. I want to find RL. We're going to go through this step by step. First of all, when you look at this hybrid model, consider it in two parts. Consider it divided in two. You look at this side as its own circuit, and you look at this side as its own circuit. This side does influence this side and vice versa. However, when you're doing the initial circuit analysis, just divide it up. So we'll start with the very first one. For our goal here is we're going to try to find I1, because if we find I1, it'll show us how to find I2. Hence, I1 times 150 will give us our I2. Okay, but we're going to do this by utilizing this equation right here. So V1 equals H11, or H, our first parameter, hybrid parameter, times our input current, plus H12, and then your output voltage. Now we already have some of these parameters. We have our input voltage, 5 volts, equals, and we already have 480 ohms, that's our input resistance. Now we don't have our current yet, our input current, so we're going to leave that I1, plus our voltage ratio, which is 4.8 times 10 to the negative 4. That's multiplied times your V2, which is right there. V2 is 100 volts. And then we can plug and chug some of this right now. We have 0.048 volts plus 480 I1, and that's equal 5 volts. Now see how minute that is? 0.048 volts. I want to go ahead and subtract it from our 5 volts over here. So, tell you what, let me make room. I'm going to go ahead and subtract the 0.048 from the 5 volts. So that's going to give us 4.952 volts, and that equals 480 over I1. Again, I'm still utilizing this first equation. I haven't gone any further than that. All right, so we're going to divide both sides by 480. And that'll give us I1, which I1 equals, and this is plug and chug in our calculator, nothing too fancy, 0.0103 amps, also known as 10.3 milliamps. Okay, so we found I1. I'm going to put this up here real quick. That way we don't lose it. So we found a very important variable, I1, 10.3 milliamps. And again, all I used was this first equation on this side of the model. Well, now that we found this first side of the model, now we can jump to the second side. Let me go ahead and erase this real quick. Second equation here to find I2 on this side of the model. This is going to be more of a plug and chug type equation, but we like plug and chug equations. Okay, so we have our current gain, which is beta 150 times I1. Now that we have I1, it's 10.3 milliamps. Okay, plus H22, or output admittance, which is 10 times 10 to negative 6, and then times V2, which is 100 volts. And I'm just going to skip to the plug and chug part because you guys got a calculator. I2 is going to come out to be 1.546 amps. Okay, so I'm going to put that right there. This is your output current. It's going to be 1.546 amps. Now, what I mean by output current, I mean it right there. Yeah, that's your I2. So we want to find the current going through our output resistor, our load resistor. So when we have our current going this way, it's actually going to split off this way and this way. So this resistance right here is, or admittance, is going to be eaten a little bit, but it's going to be very simple. So right now we know the resistance right here. It's 100K ohms because all I did was take the reciprocal of that particular admittance. And we know the voltage here because the voltage here is the same as voltage here. It's 100 volts. So if you want to find the current going through that guy for, let's say, the current at H22, it's going to be 100 volts divided by the resistance, which is 100K. Well, plug and chug that in your calculator. It's going to be 1 milliamp. That's it. So if that eats 1 milliamp, it's pretty obvious this resistor is going to get the rest. So your load current is going to be your total current minus the current going through that output admittance, which is H22. So that's very simple. It's going to be 1.546, because that's our total current, minus this current, which is 1 milliamp. Again, that's usually why this is taken on the model. It's so minute amount. So that gives you an output current going this direction of 1.545 amps. All I did is subtract 1 from this guy. So that's how much current is going through that one load resistor. Well, we know the voltage, we know the current. So now we can find R sub L. And that's going to be resistance equals V over current. So plug and chug that in our calculator is going to give us an answer of 64.72 ohms. So we have found our load resistance just by going through the analysis of this model and utilizing these two equations. That's why they're there. It gives you a chance to start doing an analysis of these two-port networks. So we already had the parameters. Now we're able to take those parameters and do a full-blown analysis. I did another example similar to this in the BJT video. So if you'd like, go ahead and go over there if you want one more example of the hybrid model. Hopefully I present you with enough information today to be a little bit dangerous. If you have any questions, please feel free to let me know, and I hope you have a good evening.